Hey, welcome everyone. Thanks for joining us. My name is John West, and many of your names out there are familiar, so thanks for coming back. We're on 2 of 8 from Michael Lewellen in terms of a series of blockchain crypto events. And last time we talked about the beginnings being Bitcoin and why that started, how that started, and how that's sort of the beginnings and the foundation. And now we're going to talk about 2 of 8, which Michael is showing how blockchains work and kind of work our way through the series. And Michael is actually teaching this at UTD. And so we thought it would be a great idea to also, well, give him some practice, but also get it out to everyone else. And so far the response has been really, really good. So thanks a lot for that. The first presentation you can go out to, is it posted on the Meetup, Michael? No, we got a question there.
I'll actually go ahead and post that link right now.
Okay. But you'll be able to go out to the Meetup and get the first presentation. So this is the Dallas Blockchain Meetup. It's actually the largest, longest, most consistent blockchain meetup in Dallas. We don't focus on any one technology. It's all technologies. Michael has been a speaker before. Michael is a local entrepreneur in the Dallas area, runs CTO of Tarski Tech. And he and I have worked together a lot over the years and actually have worked together on projects. I used to lead blockchain and crypto R&D at Thomson Reuters, and Thomson Reuters is our sponsor. Winell Mendez is also on the call, if you see her name there. So she is our connection to Thomson Reuters and does the logistics side of that and provides us food and drink while we're at Thomson Reuters, which we'll get back to someday. But so thanks to Thomson Reuters for continuing to sponsor us. And thanks for Michael for doing this again. And with that, I will turn it over to Michael and let him run.
All right. Thanks for the good intro as always, John. All right. Well, I think for those of you who are new, this might be you might not have been to this webinar before. So I'll give you all a quick recap and then we can get right into it. So this is specifically on how blockchains work, presented by the Dallas Blockchain Meetup and my company, Tarski Technologies. So let's get started with kind of where we are in the series. So like John said, this is part 2 of 8. Last time we talked about the history of money in Bitcoin, which was really focused on how that technology has kind of changed the way we use money and even the way we perceive money, and even the value behind it. And so I kind of ended that talk saying that we would get more into like how that's actually done. How does Bitcoin and blockchain technology really enforce better practices or do things that were simply not possible before? So this is really going to be a technical deep dive on that. So we really want to get into those technical details because it's crucial for understanding why blockchains are so ideal for processing payments. And blockchains, I think, are one of the most misunderstood technologies out there because it's just something that it's solving a problem that some people didn't even realize was there. Like let's compare it to like machine learning. That's an easy one. Machines are learning from data and therefore making decisions that humans would otherwise need to make. With blockchain, it's a bit different because it's doing things that we kind of take for granted, how we process payments and transactions and a lot of things that I think we're only just now starting to realize might have issues with current architectures, current centralized architectures. So I think that's why I wanted to focus this talk entirely on just how it works. What are the technical details behind it? We'll cover distributed ledgers, cryptography, consensus. So there's just a few of the highlights, but this is meant for anyone. If you don't do development or understand technology to like how it works, I'm still going to try and walk through it slowly so you can get a good idea. And we'll just start simple and then kind of build on top. And so when we're understanding blockchain, I think a lot of talks typically get into the structure of it very quickly. I wanted to kind of step back and think about like what blockchains are trying to protect. What are we using blockchains for? What are we recording? And that's, I think, where something called a transaction comes in. I think many of you know what a transaction is, but I want to really get into what a transaction is in terms of blockchain and what it can apply to. So transactions, like the very simple definition, is that they are individual operations that get recorded. We typically think about that in terms of payments, but that can be anything. It can be a Twitter post. It can be you ordering something on Amazon. It can be saving a note in an application, sending an email. Anything that is getting recorded in some way can be considered a transaction. And so with that definition, which is very broad, we create transactions all the time as consumers and digital users. So anything we do online, anything that's being recorded in a database or stored somewhere, that's a transaction that is being saved. And so we are always creating transactions. Just me creating this meetup or making any change to the meetup page or posting this link, those are all transactions that are being stored somewhere. Every time there's a change, it's a transaction. And so a few definitions for a transaction that will typically see is one, a financial transaction, a buyer and a seller are exchanging an asset for payment. And that's what we typically think of when we hear a transaction. We're just, for example, I buy a coffee at Starbucks for $10 if it was a really, really expensive cup of coffee. So that would be a financial transaction. And kind of the same as a financial transaction, but it's a bit more detailed, is an accounting transaction. So when I'm doing that purchase of a coffee, maybe I'm using a credit card. And so when I'm using a credit card, there's going to be a double entry bookkeeping event that occurs where something is debited from my account, or let's say debit card, because that'll be easier with definitions. I have a debit card, and so there's a debit against my account for that $10, and then there's a credit against the coffee shop's account for $10. And so the transaction, there's one transaction, but it's recorded in two different bookkeeping systems. So that's very important to understand for anyone that is in accounting. And then probably the most important one from a computer perspective is like a database transaction. And it doesn't just apply to databases, but that's typically where we see it. And that's a series of operations that changes data as a single atomic unit. And that's very important because if we're changing something like, if we're doing something like a payment, if we're recording that, there's several operations that are involved in making that transaction. There's several data changes that occur, not just one. But if those operations are occurring and one of them fails, we don't want to just stop in the middle of making that data change. We want to roll it back to the state it was before. And so for a database transaction, we typically want to ensure that it all succeeds or it all fails. It's either going to do the change correctly or it's not going to make any change at all, which is important because otherwise it could corrupt the data. So to understand that better, let's walk through an example of what a transaction looks like in a typical payment system. So we have Bob, who's a friend of Alice, who wants to send $10 over. When this occurs, let's say that this is going through a typical payment system. It could be Venmo, it could be Zelle, it could be a credit card transaction. It doesn't really matter. There's a payment occurring between one person to another, and there's a balance that is being tracked. So when we're doing this, there's actually going to be several operations that need to be done in order to do this transaction from a data perspective. The first thing we're going to have to do is subtract that $10 from Bob's balance. And as we do that subtraction, we need to think about how, there are certain checks we need to do to ensure that that is an operation we can safely do. For example, does Bob have a balance of $10 or more? If he doesn't have a balance of $10 or more, we should probably stop it right there. We shouldn't make any data changes, and we should return some kind of error that says, Bob, you need more money if you're going to send it to Alice. So let's check the balance. Now we see that Bob has $40. That's more than enough. So we're safe to do that operation. So let's subtract the $10, and that leaves Bob with a balance of 30. Great. What do we do next? Next, we want to add that $10 to Alice's balance. And this also means we have to check a couple things. For example, does Alice have a valid account to receive the $10? If, let's say Bob got the name wrong or the account wrong, or it's just an account that doesn't exist, then we want to reject that transaction and then roll it back to the previous state. That includes reversing the $10 subtraction from Bob's balance. But Alice does seem to have an account. It seems to be valid. So let's apply that second operation. And now Bob has $30 and Alice has $10. So it looks like we're done, but there's actually one more thing we should do, and that's save the transaction details. We need to save the fact that this event occurred, that Bob was sending $10 to Alice, because you want to have a record of that. If you go onto your payment app, you would typically want to see a history of the payments that Bob had made to Alice, so that when Alice says, "Hey, did you send the payment, Bob?" Bob can say, "Yes, here it is. Here's the time," etc. So pretty basic stuff, but very important to understand if you're new to this. So let's take a look at that and think about, okay, when we do these transactions, what could possibly go wrong? How could someone potentially manipulate the system? So we have a transaction of from, to, and the amount. There's one attack that is particularly troublesome in digital systems that are doing payments, and that is a double spend attack. So if this was a digital transaction, Alice could potentially copy that transaction, because you can copy anything in a computer system, and then replay it until Bob's balance was empty. And this is called a double spend attack. And so we need to figure out a way to prevent this. We need to make sure there's a check and balance in the system that ensures that these transactions can't simply be replayed over and over again. So typically in a lot of systems, what they do is they trust a third party to maintain a copy of a ledger of all the transactions that have occurred, to ensure that there's always a fair accounting at the end of the day. And that's what most banks and payment systems do. And this is in fact what banks have been doing since before computer technology was a thing. They've just continued to do it as computers have become more prevalent. So these are essentially centralized ledgers that are used to verify double spending does not occur, as well as verifying ownership, verifying other payments, all sorts of things. And this has worked pretty well over time, but there's definitely been issues that come up with having this so centralized. You can face numerous issues. As a single point of failure, you can see a lot of hacks that will typically occur against banking systems. A lot of fraud can occur when there's only one group that controls a ledger. There's either the group itself or people within the group or the organization can potentially commit fraud, because there's no one else that can really see that centralized ledger or modify it other than them. And then in general, you see a lack of cooperation. With a bank, they don't want other competing entities to use the same payment system they have. They want their competitive advantage. So you're typically not going to see them share technology or allow open access to their systems, even if it's for the benefit of the whole, of everyone in that economy potentially could benefit from that. It's not in their individual best interest, so it simply does not occur. And that's not the bank's fault. That's simply the hand they've been dealt. But it does mean that payment systems in today's day and age typically do not benefit the customers as much as the technology has the potential to do. So how do we rectify that? How do we get past this? Well, this is where decentralized ledgers come in, or distributed ledgers, I should say, because distributed and decentralized are different things, and I'll get more into that as we talk through this. But a distributed ledger is different because it allows any participant to access and maintain their own copy of the ledger. So as opposed to that bank example, all of these nodes, all of these participants in this payment network all have a copy of the ledger. And so they all operate, and these nodes essentially are just computer programs that run and communicate to one another in a peer-to-peer network. So they exchange updates with one another and keep each other updated. So this is kind of more in line with what the internet is today, but even more decentralized, or I should say distributed. And so by removing that centralized party, you have no single point of failure. If node A, runs into an error or gets shut down, the ledger itself will continue to operate just fine. And this is something that is, like a bank's worst nightmare, is going down or having some kind of a network failure, and then their customers can't do their payment transactions. And this has occurred a lot in the past. With a distributed ledger or distributed payment network, you don't have that problem, because if one or two nodes go down, the rest of the network can continue to carry on because they all have a full copy of the ledger. So this makes the system far more resilient. However, if we want to actually do payments in a trustless manner, we're still missing quite a few pieces. One, we can't verify that payments came from the correct owner. There's no way to know if Bob is sending the payment to Alice, or if someone else is pretending to be Bob. We can't reach consensus on the correct ledger. If node A proposes a change, should the rest of the nodes accept it, reject it? What's the criteria for that? And then in general, preventing malicious nodes from cheating. If node D is going to try and falsify payments and send it out to others, how do we prevent him from doing so, from corrupting the ledger? So we still need to think about those particular issues, and that's where blockchain technology has to start, really where blockchain technology starts to address those issues. So let's look at an example of one of those potential attacks with the system we have now, with just that distributed ledger. Let's say Bob is sending that same transaction to Alice, but someone else is listening. Eve, who is an attacker, is listening to Bob's network and is able to intercept that transaction before Bob can send it to the ledger. And what Eve does is, because again, these are computer programs and you can access and modify data in a computer rather easily, especially if it's not properly encrypted, what she can do is she can actually change the name, the recipient, from Alice to Eve to herself, and then resubmit that transaction to receive the funds. So this is what is called a man-in-the-middle attack. Eve is in the middle, intercepts a transaction, and then sends it in order to gain funds. So this is something that if we want this to be a truly usable payment network, we have to control for this sort of thing. So what can we do? What technology is available to address something like a man-in-the-middle attack? Well, that is where cryptography becomes essential. And that is really that, cryptography puts the crypto in cryptocurrency for a very good reason. And I'll get into that right now. So cryptography itself, what is it? There's a lot of good definitions you can come up with, but what it is for is protecting communications and data. The first instance we saw of cryptography was in World War II, where it was used for encrypting military communications. You could even consider cryptography as existing far before that for anyone that was trying to write messages in code and keep them secret. But I would say modern cryptography really started to develop in World War II, because you had things like the Enigma machine that was built by the Nazis and the code breakers at Bletchley Park that were able to decrypt that traffic for the Allies. And many people actually say that World War II would have been several years longer without some of the cryptographic breakthroughs that we saw from code breakers working for the Allies. It was responsible for a lot of victories on the Western Front in Europe, and it was also responsible for the turning point in the Pacific War at the Battle of Midway. We were able to decrypt Japanese communications and figure out they were launching an attack. So even before computers were really a thing, in fact, the first computers were used for breaking code, cryptography has been incredibly important. More modern crypto to the present day is a technique that really combines both math and computer science to protect systems from attackers. These encryption techniques are what we use on the web to protect our traffic so that we're not going to be spied on by anyone who's able to listen to our communication or tap in. And so again, crypto really is important for how blockchains work, and that's why cryptocurrencies are named the way they are. So what kind of cryptography is really specific to blockchain? Well, one is digital signatures, and these are very important. These are public and private key pairs that we can use to identify people and the transactions that they are creating. So in this public-private key pair, we have a public key, which is used for identification. It's kind of like a username. You can share your public key with whoever you want and say, I'm this public key, and that's perfectly fine. You can even put it on a billboard if you want to try and get some potential crypto payments. And then a private key is used for security, and it is kept secret like a password. You don't want to share your private key because it is crucial to keeping yourself secure. And what you do is you can use a private key to sign a message, which creates a digital signature that is unique to that message. No one can copy that signature and put it on a different message. That simply will not work. It's unique to that message. And anyone can then verify that digital signature belongs to your public key. They don't need to know what your private key is. They just need to know your public key. So this is incredibly powerful for verifying messages online and making sure that people can sign things uniquely. It's not like signing a piece of paper where someone could try to copy and forge your signature. With this, if you modify anything, it invalidates the signature. So it's incredibly powerful. And then one other technology that is just as important, if not more so, is hashing. Hashing functions are used to accept any piece of data and then create unique fingerprints for that data. It's a great way to identify what kind of data you're looking at and whether it matches what you're expecting. So hash functions will accept any kind of data and then create these unique IDs called hashes. The same input will always produce the same output. Doesn't matter if you gave it the entire Library of Congress, it would give you the exact same output as if you gave it the same Library of Congress again. And then if you change one letter in one page, in one book in the entire Library of Congress, the output would be entirely different. It wouldn't look similar at all. And that makes hash functions almost like practically impossible to forge. They're very difficult to reverse. And when I say difficult, I mean practically impossible, as in if you had maybe more computer power than existed in the last 100 years, maybe you could break certain hash functions, but for the most part, current hash functions are practically unbreakable. And so with hash functions, we can easily compare data to see if it's the same, and it will always be correct. So let's dig into how we apply this. So let's look at digital signatures first. Let's take Bob, who wants to send that same payment, and give him a private key, which he can then use to sign that message. So there's a unique signature from Bob that's been added to the transaction. And now when Alice tries to grab that transaction and replay it, she runs into a problem because that signature is unique to that message. And whenever you try to modify a transaction with a digital signature, it invalidates that transaction. And so Eve can't generate a valid signature, and therefore the attack fails, and she cannot pretend to be Bob and get payments from transactions he's sending. So this is the first way that blockchain technology is able to really enhance the security of transactions that we send online. But there's something else we need to do. We still need to identify transactions. We can verify it, but we want to look it up. We want to know, is this transaction that Bob sent the same one that I am looking at in the ledger? We want to be able to compare and contrast, especially if we want to be able to detect if double spending is occurring. So how do we do that? Well, we can use hashing functions to uniquely identify those transactions and then easily look it up in the ledger. So let's take that same transaction that we have and let's put it through a hash function. And what that will do is essentially take all of the inputs that we're giving here and produce a unique output. And note, this is an oversimplified example because there's actually a lot of complexity that goes into how blockchain transactions are hashed, but this gives you a very good idea of how the technology works. So what we'll do is we'll take that hash and assign it to the transaction. So we now have a unique ID for that transaction. That very long string of text is effectively a good example of what a hash would look like. One quick question from Dennis Ellis. Is Alice's name / public key part of Bob's signature when he sends it? Yes, I did not mention that, but yes, her public key is part of the transaction because that is how Bob identifies that Alice should receive those funds. And the reason that's important is if Alice wants to then send those $10, that same $10 to someone else, she needs to use her private key to send it. So that's why we're associating it with her public key. So same thing as like if you were going to send a payment on PayPal to someone's email that's associated with their account, which they can then use to send it to someone else. So good question. I'm glad you asked that. Okay, so once we have this, we can now use that hash to look up that transaction in the ledger, in that distributed ledger. So this is great. Now we have a way to uniquely identify transactions and ensure that we don't get duplicates. That typically means that someone is trying to do a double spend attack. But we do have one problem still. We can quickly compare individual transactions with hashes, but comparing like a large group of transactions is very time consuming. If we had 1 million records in the ledger and we were trying to see, hey, is your ledger the same as mine? Trying to compare 1 million records against 1 million records is going to be very time consuming, even for a computer. That's what is called an O(n) squared operation. So it's exponentially difficult. So that's where Merkle trees become essential. Merkle trees were created by a man named Ralph Merkle back in the 70s as a way to quickly compare large groups of data. And it's one of the crucial building blocks for blockchain. And let's show you exactly why. So let's say we want to take the hashes of all transactions. We take the hash from this transaction from Bob, and we, say there's another 3 transactions that we want to compare in this group. We'll take all those hashes, and what we'll do is we'll form a tree with those hashes acting as the leaves of the tree, the very tip of the tree, and we'll start to combine them into branches. So first thing we'll do is we'll hash each pair of nodes, each pair of transactions into a new combined hash. And so this is a hash built from the input of A and B to form E, and then same for C and D and F. So if we changed B or changed A, then E would be entirely different as well. And we would continue to do this no matter how many transactions we were talking about until we got to one final hash, and this would be called the root hash. And now we have a single hash that represents all the hashes of the transactions that we are trying to compare. So this is very, very powerful because now we can ensure that no unauthorized changes are occurring. So let's think about what happens if there is a change. Let's change that transaction to say $10 instead of $13, let's say. That's just a very small innocuous change. And we can see that the hash is actually a bit different. I've changed the hash that's generated from that transaction, which then changes the hash that we are adding into the tree. So we now have Z instead of A. And what happens is this creates a trickle effect. As soon as we change that, every other node related to it changes so that the root hash is entirely different. If just one hash is off, the root hash is going to be entirely different. And that means that you can't get away with any small innocuous change without invalidating the root hash. And the reason that we want to do this, instead of hashing all the transactions together, the reason we use this tree structure is that we can individually identify transactions that are part of the tree by just plucking them off and then adding in the nodes that we need. So that makes it very easy to compare individual transactions within this entire structure. So now this large list of transactions can never be tampered with because we can always check a Merkle root hash and know if it's correct or not. But one thing we're still missing is a way to reliably order the transaction. This tree structure is great for verifying that transactions are in, these are the correct transactions for the ledger, but it doesn't tell us what order they came in. And that's important because if Alice wants to send a payment from Bob to someone else, we need to be sure that the payment from Bob came first and not after. So let's see how blockchains do that. And this is really where the blockchain comes into play. So we need to actually build a blockchain from what we've gathered so far, which is a Merkle root and a list of transactions. So what we do within a blockchain is we group transactions together so that we can establish an order. And this order is going to be based on some kind of time frame. So we'll group them from the same time period, for example, 10 minutes with Bitcoin, into a single block. And this is kind of like having a page in a ledger book. You might have a page that represents all the business you did on Monday in your ledger book for your home finances or your business finances or whatever. Same thing applies to a block in a blockchain. So what goes into that block? Well, the first thing is let's take the transactions that we have and create a root hash and put that into the block header. So that gives us a way to uniquely identify all the transactions that are within that block. Next thing we want to do is we want to create a timestamp. So now we know when this block of transactions occurred. We also want to add in what is called a nonce, and this is very important for mining. We'll go over this later on, but just know that a nonce is crucial for securing a blockchain. And then last but not least, in fact, most important of all, we want to include a hash of the previous block, because this is where we get into the chain of a blockchain, because we can now start forming a chain based on all the information that we've now provided. So let's see what that looks like. So by including the previous hash in each new block, we can create a virtual chain between every block since the first Genesis block. So that previous block hash references block 100, which also references the previous block hash from block 99 and block 98 all the way to block 0, which would be considered the Genesis block, the first block of that blockchain. So this virtual chain extends all the way back to the beginning. And then same thing for whatever comes after. What comes after block 102 would have the hash of block 101 as a way to link them together. And this is very important. This is where blockchains are so crucially secure to ensure that no unauthorized changes occur anytime in the past. So let's do the same example. What happens when we change the transaction again? So let's modify those transactions in block 101. Let's say it was the same innocuous change of changing $10 to $13. What happens then is we will invalidate the Merkle root hash. And so that will change within the block 101 header. And because we're hashing the entire block, that also means that the previous block hash is invalidated. And that means that every block that comes after block 102 will also be invalidated because block 102 will be included in the next block as the previous block hash. So this means that any change to a transaction, no matter where it occurs, as long as it's within the blockchain, it will invalidate everything that comes after. And this is what makes blockchains so secure. The chain enforces an immutable order of transactions that can never be tampered with once that block is created and added to the chain. So this is really where I think you see the structure of blockchain at work and where the name really comes from, the fact that these blocks form a virtual chain. So we now have an order, but we still have one problem left, and that's the fact that we need to ensure an attacker can't simply recompute a new chain of hashes to make changes, because computers are very powerful nowadays. So what if someone tried to go back and just recompute the hashes for those 100 blocks to make one small change and then propose the new block and make sure that everything was in line? We need to make sure it's difficult for someone to go try to redo hashing that was already done. And this is where proof of work comes in. And this is going to be done by nodes called miners, which are responsible for forming new transactions into the next block. And this is where mining and that whole thing comes into play, which is, I think, sometimes not well understood by people that are new to blockchain, because it's such a strange concept that some people think that miners are trying to do that Bitcoin is very computationally intensive. And it requires a lot of work to run. It's not actually forming the transactions or processing those payments that is difficult. It's this proof of work. And so what proof of work is essentially miners trying to calculate the nonce for a new block, which is actually it's not anything necessarily complex. It's just a very hard math problem that takes computers a certain amount of time to guess correctly. So the more computational power you have, the faster you can potentially guess, which is why miners are so obsessed with getting the best hardware and having the most computational power, because it lets them guess that math problem a bit faster than other people might. But it doesn't have to do with processing payments. It just has to do with creating the new block in a way that is difficult so that previous blocks can't be recomputed easily. In fact, it's almost impossible with this sort of system. Because what we do then is we take that nonce and we add it into the block header. So,
hey, Michael.
Oh, go ahead.
I was just going to add, this is kind of, it is the reason I think, or that Bitcoin gets criticized for being so, using so much electricity. And part of it is that it does use a lot of electricity, but people look at this and say, well, it's wasted because you're just calculating something that has nothing to do with verifying the transaction. You're purposely slowing the network down and making it hard. It's very wasteful. And that's how people come to that conclusion, that it's very wasteful. And the flip side argument is, well, actually, that's what provides the security. It's very hard to compute and it takes a lot of energy. And that's why blockchain and Bitcoin in particular are so doggone secure. And people that argue proof of stake will say it's not necessary, but it hasn't been proven yet, and only time will tell. But anyway, I just thought I'd throw that in there for folks.
Yeah, that's definitely a good thing to emphasize, because that is, mining is about being difficult. It's not about being easy or efficient. So that criticism of well, I think it's a fair criticism in the sense that yes, it takes a lot of electricity to secure Bitcoin. It's not around the way that transactions are done. But yeah, that's a good point. And then basically, so for doing all of that work, the reason that miners are willing to go to all of that effort to process transactions is because they will typically be rewarded with transaction fees and new coins, which incentivizes them to continue to invest in the network. And this is really where I think blockchain goes beyond just being a good technology. It's also very good at economics and game theory, because just like people that mine for gold are willing to invest a lot of time and effort into it, a lot of crypto miners invest a lot of time and effort into effectively securing these blockchains, whether it's Bitcoin, Ethereum, or anything else that has proof of work. So they're incentivized to protect that network and act in its best interest because so much has been invested in that. So it's one of the reasons that I think blockchain goes beyond just being good technology. It's a good way to incentivize collaboration, because people are incentivized to put in the effort to protect that system because they effectively have so much at stake. And so as that nonce is calculated, we adjust the difficulty, because if more people have more computational power, we want to make the nonce a bit more difficult to solve. And then same goes for if mining power drops off, we want to make it a little bit easier, because the point is to make that block time pretty consistent, around 10 minutes in the case of Bitcoin. Different block times apply to other blockchains as well. And so the true ledger is then decided by the longest chain, which has the greatest proof of work invested into it. So other people could potentially try to create their own blockchain with their own version of transactions that possibly benefits them. But if the majority of the network is not putting their work into that chain, then it's always going to fall behind the longest chain, which has the greatest effort. So that's typically how blockchains create really a true ledger that everyone can agree on, because everyone's investing effort into that. They're essentially adding value to it every time they try to calculate the nonce and create a new block. They're adding more work onto it, and there's no way to there's no effective way to recompute that entire blockchain and then try to catch up to the existing one, because that longest chain is always going to be faster because it has so much work already built into it. It's always going to be ahead. So that makes blockchains incredibly secure. The only way you can really beat it is if you can gain a majority control of the mining power, around 51%. This is where the famous 51% attack kind of comes from. And even then, there are difficulties there, in the sense of if you do successfully create an attack against the network, you might even undermine your own profit, in the sense of if you hacked Bitcoin successfully and you're trying to get Bitcoins, the value of Bitcoin would probably drop because that 51% attack occurred, and there's no way to do it quietly. As soon as a 51% attack occurs, anyone who does mining will know about it. And then who decides okay, Andy is asking,
hey, Michael,
who decides the value?
Oh, sorry.
Oh, go ahead.
Go ahead. No, I have a question. Let Andy go first.
Okay, gotcha. So Andy's asking, who decides the value of the nonce that needs to be calculated? So that's a good question. So that is decided by the algorithm. And what it effectively does is it says, hey, here's a nonce that you need to generate for, basically it's actually using hashing. And it basically says the value that you put into a hash needs to come out with a certain number of zeros. And so it's basically saying, figure out what the right input is, and then once you figure out the right input that gives me the right answer, then you can put that input into the block header. And it's a great, elegant solution because it's not very difficult. It just takes a lot of time. There's no way around it. You have to guess, and that means computers just have to keep churning through possible answers to that problem until they get the right answer. So it's procedurally generated, and then the difficulty of how long it will take for that nonce to be generated is automatically adjusted by the network, typically every certain number of blocks. In the case of Bitcoin, I can't remember how many blocks, but you'll typically see an adjustment every few months, depending on how many miners are in the network at that time.
Every 2 weeks, I think.
Yep.
Hey, here's a question. On the 51% attack, I've never dug into this or studied this, but I've heard people say, well, really, some attacks are 34%. It's not 51%. Some attacks are 51%. Some attacks are 34%. Have you ever seen that or heard that, or do you have an answer to that?
Yeah, I've heard of a few people talk about that. And propose that. And it's difficult to know if you don't have a real life example to show, but I think in the case of the 34% attack, that I've heard is typically done, it's in conjunction with other attacks in the sense of what you can do is if you can split off a certain portion of the mining power, like let's say and I think one example I've heard is China. Let's say China, the country, is able to cut off a lot of the miners within that country from the rest of the network. Well, then the total mining power available is reduced. And even if you have a lower portion of the total mining power, because you've kind of blocked out a large number of miners, you can effectively take control of the network with just like 34%, because you could be blocking out another third that isn't participating, and so you can kind of overwhelm the ones that are left. So without a majority, yeah.
So if you cut it in half, and then you only need 25% of the original to do a 51% attack.
Yep, exactly. And that's why centralization is kind of a hot topic in the industry, where we don't want to see any one miner or group of miners gain too much control of the network in terms of mining power. In fact, what you'll typically see is miners will typically get together in pools, because that increases their likelihood of winning a block and splitting the reward. And what you'll sometimes see is if one pool is getting so large that it could control close to 51%, or just an uncomfortable large percentage, you'll typically see miners move between pools and go to other pools when that is starting to occur. So the ecosystem likes to self-correct for that sort of thing, but it's always something that the community is watching out for, because it's always a possibility, but it's one that becomes more difficult the more total power there is, because it requires someone to control a massive amount of computation, and the cost of getting that computation will probably exceed the value of a successful attack. Okay, so TM is saying which party creates the Merkle root under what circumstances? 2, who creates the nonce? I think I already answered that. That's just procedurally generated by the blockchain itself. The value that needs to be solved for the nonce is procedurally generated. The miner is the one that eventually comes up with the correct nonce. On the first question, the Merkle tree root is constructed by the miner. So this construction, let me go back a bit. Yeah, this construction is done by the miner. And everyone in the network will kind of validate that those transactions are correctly complete. And there's typically a very good way to check that. But the miner is the one who's going to be assembling those transactions and putting them in the block. So they're essentially responsible for that part of the process.
I think it's interesting, Michael, that essentially every miner does that. They collect transactions and put them in a block. So there's a whole bunch of potential blocks out there, and then it's the one that solves the math problem that actually wins, and all the other blocks get thrown away, and then that one wins. So thousands of potential blocks get created, and one of them wins.
Yep.
Right?
And that's entirely based on the nonce. Yep. And where do the miners get the transactions? So they have nodes that are listening to the network and basically pulling in those transactions. So it's a peer-to-peer network. So if you send a transaction to a blockchain node, it'll send it to all the nodes it has connections to. Those nodes will send it to more nodes, and so it'll eventually propagate to those miners, and they'll include it in their next block. And what you typically see is sometimes there is inconsistency between different blocks as far as what transactions are included. And typically it's done by whoever's paying the highest transaction fee. Miners will typically say, they'll just automatically say, if you're paying more, if Bob is paying more to send his transaction than Alice is, then Bob's transaction will go in first. So typically, if you want your transaction to be included in the next block, for sure, there are tools that will tell you pretty much the right transaction fee to send that will essentially guarantee it gets processed. And even if you don't get your transaction included in the next block, it will typically get included in the next one or the one after that, as long as you paid a reasonable fee, as in you didn't pay like it was so low that no miner would ever bother processing it. And that is an issue sometimes, where people will put in transactions that have such a low fee that they just hang forever. And that's one issue you have to be careful with when you're doing transactions. Most wallet softwares will try to will calculate the fee for you to ensure that never happens, but it's something to be aware of if you're working with the technology at the technical level. And yeah, if mining stops, the blockchain dies, because effectively, and I would say by dying, it just doesn't grow. The existing transactions will still be there, and immutable as long as no one tries to mine the whole chain over again and add a change in. But yeah, mining is always going to continue. In the case of Bitcoin, it's continued since the Genesis block in 2009. Every 10 minutes, a block is created, no matter what. And that's why having it decentralized is so important, because if a group of nodes or miners get shut down, the network will continue as long as there is one miner or one node still running. And there's thousands of them. So, and they're scattered throughout the world. So trying to shut it down effectively would be practically impossible.
And it would die if there wasn't a financial incentive.
Yep, exactly. So the value has to be there.
Yes.
And yes, a miner made money because he got to create the block. So he gets money from parties whose transactions got included in the block. Yes. Yep. That's exactly how it works. So they get both newly generated coins. In the case of Bitcoin, they get a certain amount, which typically is modified over time. There's like a halvening that occurs every once in a while where the reward is split in half because it's trying to reduce the supply over time. But they'll always get transaction fees. And so even if the blockchain doesn't want to issue new coins, like say Bitcoin reaches its 21 million max, people will still mine because transaction fees will be available. Awesome, glad it helps. And then I think there was one more question from you. How and when does that blockchain get connected to the next one, and at what point? Just to answer that really quick. So the block gets connected to the next one when that block is added. So whenever every miner is going to include the previous block hash in their current block, and then whenever one of those miners wins, then that's when that chain occurs. Will only one miner win? Is it possible for multiple miners to win? It will always be one miner in terms of basically like a pool of miners could win, but that's because they're working together to generate the same block. So multiple miners can win if they're working together, but it's always going to be only one group or one block that will win. All the other blocks that are being used separately will be different.
Isn't it technically one miner solves it, but he's in a pool, so he shares his winnings with the other people in the pool?
Yeah, that's typically. Yeah, I think so. No. But yeah, the pool will have software that you point your miners to that will essentially detect when someone wins and then distribute the funds to everyone. All right. Oop, I didn't mean to go that fast. All right. Any final questions? Because this is this is definitely the more technical part to make sure everyone feels comfortable with. Going once, going twice. All right, let's keep it going. So now let's kind of just look over like what this looks like. And yes, there will be a recording. I will be posting that to YouTube. And how much can a miner make from a winning block? That depends. If they're not part of a pool, then they will make 5. I forget what. Actually, let me look at the block reward really quick. Real quick. Uh, 12.5 Bitcoin, which is quite a bit. So, and that's just for the block reward of new Bitcoin. They'll also get transaction fees. So it's a very large amount. 12 Bitcoin is right now, going to USD, that is about $117,000. So it's a good takeaway, but that's typically why people work in pools, because it's very difficult to get that block on your own. So typically the pool will win that block and then distribute it amongst all the miners that are participating.
I think it's
Oh, okay. I was looking at the wrong article.
6. Yeah.
Okay.
6.25. So it's about 60,000.
Okay. Still, yeah, it's a pretty good payday if you were able to get that yourself, but it's very unlikely nowadays. You used to be able to when it was like very early days, like 2010. But I mean, ever since like 2012, 2013, it's really been impossible to get a block on your own. You've had to be part of a large mining pool. All right, so let's see. So blockchains in practice. So since the creation of Bitcoin, we've seen a lot of new blockchains that have been introduced. They go through a lot of numerous changes, and so I think it's good to look at them to understand some of the differences on how Bitcoin and really like new iterations essentially of Bitcoin have been evolving. So let's look first at Bitcoin. So it was created in 2009. As I've said before, it has a block time of 10 minutes. So transactions are collected over the course of 10 minutes, and then a new block is created and added to the chain. The hash algorithm, which means the way that it hashes the nonce, is SHA-256, which is important because if you're getting a miner, it needs to be able to support the SHA-256 algorithm. And so people will typically create miners that are custom built for specific hashing algorithms. It uses proof of work as consensus because it does purely mining. And then as far as transaction types, it supports payments and scripting. So like scripting being like doing some kind of a custom transaction that changes data in some way other than sending Bitcoin. But for the most part, people use Bitcoin transactions for payments. There are use cases for doing scripting with Bitcoin. In fact, there are some systems that will even tether into Bitcoin, such as Factom, that embed data into it directly. So it's definitely something you can build off of for like creating immutable data anchors. But for the most part, Bitcoin is focused on payments. It was originally built for payments, and the modifications that have occurred since, I would say there hasn't been a lot of work on creating a general custom scripting language for doing. Bitcoin's focused on payments. That's the main thing. I can get into details on that, but that'll get confusing. And then Peercoin, you might not have heard of Peercoin. Peercoin is it's not a very big cryptocurrency today. It's probably like top 500 in terms of market cap. Let me actually look up the market cap right now. It's got like a $6.5 million market cap. Not very big, but the reason I'm talking about it is because it's one of the first. It was the first to do proof of stake, which was kind of trying to go beyond proof of work and try to figure out a different way to handle consensus, because it was concerned about the processing effort that's being put into making sure proof of work secure. And so what it actually does is it combines both proof of work and proof of stake. So it's so basically what it does with proof of stake is it rewards users for holding coins, and the longer they hold those coins, the more the more mining power they have. That's considered more efficient than proof of work. It still works in tandem with proof of work, and it's a bit complicated, so I won't get into it here. But the main reason I'm mentioning it is because it was the first time that people were looking at different consensus algorithms beyond just mining. And since then, we've seen a lot of other attempts at making proof of stake work in blockchain protocols. A lot of the time still working with proof of work mining, but it's the first to really popularize the idea. And I think a lot of solutions are extended from Peercoin originally. And then another one that's important, and we'll be talking about more in later talks, is Etherium, which was created in 2015. Its block time is actually far faster, 15 seconds. And the reason that they're getting away with the faster block time is that they've actually had ways to address the idea of blocks forking. So the reason that Bitcoin is 10 minutes is because it needs to have latency so that miners can detect if a new block, basically, they're working on this block, and then eventually they'll probably hear that someone else has solved the block, and so they throw away their work and they start working on the next block. If you don't give enough latency for a miner to respond to that, then sometimes they can get confused about which block they're working on, and that's where forking can occur, and people can get, miners essentially don't have time to figure out which block to work on. So that's why Bitcoin has it as 10 minutes. And you can see Peercoin has improved on it, but they only got down to 8.5 minutes. Others like Litecoin did 2.5 minutes, but Ethereum really accelerated things by doing 15 seconds. And they have some specific features called uncles that are able to address that. And I'll get into those more in a separate talk, but just know that Ethereum was able to really improve their block time with some improvements to the way blockchains are created, or rather blocks in the chain are created. It uses a different hash algorithm called Fhash, and the reason that was done is because Ethereum uses GPU miners specifically instead of ASIC miners, which are kind of custom built for SHA-256. And the reason they wanted that is they didn't want Bitcoin miners to be able to come in and dominate the Ethereum mining space. They wanted it to be a separate thing. So that's why hash algorithm is important. And any blockchain protocol you look at will typically have a hash algorithm, and many hash algorithms are a lot of the times they will sell a unique hash algorithm that isn't dominated by ASICs as a pro, because it's easier for me at home to use a GPU to mine cryptocurrency than it would be to buy ASICs that are kind of custom built for it. So it's considered more accessible to individual miners. Consensus is proof of work, but they are working on proof of stake in Ethereum 2.0. Again, something we can talk about more in the future. Colin is asking about Cardano in a future talk. I will write that down because I do like Cardano. I haven't thought about including it, but if you are interested, I certainly can, which is another blockchain that we could talk about. And it, like Ethereum, is focused on not just payment transactions, but smart contracts, which are ways to do custom transactions for anything that you can code in a Turing complete language. So it's the idea of taking transactions beyond just payments to be more general purpose, which is really, I think, where a lot of blockchain capabilities get unlocked. When you say we're not just going to worry about payments, we can do any kind of transaction that you can define in code. And Bruce is asking, should a DOS attack against the Bitcoin blockchain consist of someone doing millions of scripted tiny value transactions that can overrun the capacity of the current set of blocks? A good question. Also, really quickly to Barath, POW is proof of work. So it's just a shorter way to say proof of work. So for Bruce, that is a potential attack, but it's one that Bitcoin mitigates, because doing those millions of tiny scripted value transactions, in order to actually overrun the capacity of the current set of blocks, you would need to pay fees that were high enough that miners would be willing to include them. So you can certainly try and spam the network with tons of tiny transactions, but if you're not including fees that are high enough to be acceptable to a miner, they'll just be ignored. They effectively won't do anything. And what you will typically see is if someone is going to try and DDoS the network effectively, they would have to put in so much money to generate transactions that with fees that are worth processing to a miner, that it would be incredibly prohibitive. And this is another area where Bitcoin is very effective, because Bitcoin and many blockchains, because it says that for individuals to submit transactions, they're going to have to do a little bit of work or add a little bit of value, which is essentially let me actually look up a standard Bitcoin fee for you right now, because it can fluctuate. It's essentially a market let me see here. So it's essentially for a market for, what will it take for me to include my payment in a transaction. And so let's see, Bitcoin average fee is 2.335 USD. So it's about $2.33 to send a Bitcoin transaction, which it sounds like a lot if you were making, let's say, a coffee payment. But if you were sending $2 million, let's say, or even $1,000, a $2.33 fee is pretty good, because a bank would typically charge you a percentage fee, which means if you sent $1,000 and they're charging 1% fee, that's $10 instead of what this would be, $2.33. The value of the transaction is not being charged for, just the transaction itself. What it's going to take for a miner to include that in the next block. And so, yes, the miner does get to choose which transactions are included in the next block. And it determines which transactions are included in a block by how much fees people are paying, typically. They can choose to use other metrics to determine which transactions they want to include. But for the most part, miners will simply say they'll just sort it by who's paying me the most via fee and work down from there. And again, it's because it's a market price.
And that works good for Bitcoin. There's nothing nefarious or whatever that can happen. That would not work well for something where order is important. So stock trading or things like that, gaming, where the order is a lot more important and can't be controlled by a miner. And that's why some
Yeah.
of the blockchains do things differently.
Yeah, and I'll say the order within that block time as well, because if you're doing let's say a real estate transaction, 10 minutes, the order in which it occurs within 10 minutes, or if it takes a block or two to be included, that isn't going to be crucial. But things that I would say real-time order is where you're going to have an issue with potentially like a 10-minute block time where miners can potentially change that order. Yeah, domestic wires cost 15 to 30, can take hours, requires paperwork. Yep, exactly. So yeah, you see a lot of advantages with using something like a blockchain. And again, Bitcoin is the first blockchain or cryptocurrency out there. There's many blockchains and cryptos that are far faster, far more efficient. Bitcoin is still dominant just because it's the first one. And there's also ways to improve blockchain or Bitcoin payments with things like payment channels. But overall, you still see a very big improvement over existing payment systems with these sorts of blockchains. But now that we're talking about order and other things, I think that's actually a good segue, because I think there's also a very good discussion to be had about what blockchain means in terms of the other ledger technologies that are out there.
Hey, Michael, FYI too, we're at the top of the hour, so.
Gotcha. All right, I'll accelerate through this one because I think the chart speaks for itself. So typically what you'll see is other ledgers don't offer the same level of security that a blockchain does, but you also don't want to use a blockchain if a less secure ledger will still do just fine. So typically the way that payment systems are done nowadays are typically with like a database, SQL, NoSQL. The Swift network, I'm sure, uses some form of database to handle its payments. And then within that, something that you've seen develop over the last 10 years, especially as blockchain technology gets popular, are DLTs, distributed ledger technology. And so you have the quantum ledger database from Amazon that's considered a distributed, secure database. Corda is they've been called a blockchain solution, but really they're a DLT. They don't use the blockchain data structure. And then Hedera Hashgraph, which is a local Dallas company here, the Hashgraph is a DLT because it doesn't use a chain of blocks. It uses something, a DAG structure with the Gossip protocol. So it's a different way to solve the same problem. And then within that are then blockchains like Bitcoin, Ethereum, Stellar that are using this series of blocks as a way to secure transactions. And so ultimately deciding which of these is best is depends on the trade-off for your use case. Blockchains that are decentralized are typically going to be the most secure, but if your use case doesn't require like that level of security, then like a less secure DLT or just a normal data store might be better, just because it's going to be more scalable and it's going to be more simple. So blockchain features, I'll spin through this as well, but transactions are immutable. They cannot be tampered with. Hash functions make sure that you can't modify anything, and so they are censorship resistant and they are transparent. So it's great for use cases that require that. They're verifiable. Transaction rules are guaranteed. No one can cheat because you have things like digital signatures to ensure that someone who's sending a transaction is actually authorized to send that transaction. And so this means we can guarantee ownership and other enforceable rules that we build into the protocol or as a smart contract. It's decentralized, so you have no single point of failure. Anyone in the network can store and update the ledger to ensure it's always available and auditable. And one point I really want to get across is decentralization is not just about running nodes, but it's also about how the network is governed and how the software is maintained, especially as open source. You can do blockchains that aren't open source, but what I've typically seen is that you can run a node, you can have a lot of people run nodes, but if they aren't making the decision of how that node is constructed or the code that's included in that node, then they don't really control what they're running, even if they can just choose to run it or not. So that's, I think, an important thing to understand. Decentralization goes beyond just the network structure. It's also governing that network and maintaining it with software updates. For example, Satoshi Nakamoto has left effectively the Bitcoin community since 2010, but developers are still maintaining it and growing it because there's no dependency on just one person. So that means it's reliable, that means it's successful, and most importantly, it means that people are willing to collaborate on that platform effectively by contributing to an open source community. And it's one of the reasons that I think blockchain technology can really grow fast, is because if anyone can contribute to it or be a part of it and understand it inside out as far as the source code, then it means that large corporations to small individuals are able to essentially be on the same playing field and participate in the same community, which is what we've seen with Bitcoin, Ethereum, and many other open source blockchain networks. You can say that I think proprietary technology will still always have a role to play, but I think open source technology is where we're going to see the most innovation occurring, because it has a lot of things that can accelerate the process faster than a single company could. So in conclusion, blockchains are revolutionary because they're immutable, they're verifiable, and they are decentralized. And the number of online transactions that we create is now at an all-time high. Now that we're all staying inside, I mean, things that we might be saying or doing in person are now all online, and they are all transactions. No matter how small or insignificant they may seem, they are a transaction that is typically stored in someone's database. And that transaction is going to be more increasingly responsible for defining who we are and the value we provide, especially if you're working from home. Every little thing you're doing from home is probably recorded as a transaction and used to evaluate you as an employee and the value you provide to your company. And the same can be said for an influencer on YouTube who's posting videos and getting likes and views, and those are transactions that reflect on their value as a content producer. So as we moved into a digital world that's currently very centralized, where companies like Google and Facebook and companies like Oracle control a lot of the database software out there. Again, a good example of a company where if you buy the software, because it's not open source, you don't control it. You have to do the updates that they require you to do. You have to pay the fees that they require of you. If you want new features, then you have to work with them to get them. Generally, all that data is centralized. Even if you are maintaining the database yourself, you don't really control it if you can't change the software. And blockchains really offer individuals and companies, I should say, a way to not just use transactions, but participate in their creation and the way they are created. And that's very, very important, I think, for anyone that wants to understand transactions and really depend on them for their livelihood or the way they interact in a large digital economy. So blockchain really fosters the kind of trust and collaboration that I think is vital for keeping the internet open and secure. It's why I got into this technology in the first place. It's why I've stuck around for almost 10 years now, because I think this is going to be crucial for getting the internet to the next step without sacrificing individual freedom or making systems very unreliable. I think it's required to really get us to that level of trust that lets people depend on the internet for their livelihood. And so that's our talk. Yes, I'm glad the audio is better. Thank you. And next time we're going to be talking about financial assets, how we go beyond cryptocurrency and actually create what a lot of people are now calling crypto assets in order to essentially I think transform the financial industry in a way that I think is going to be very, very incredible to watch. And it's one of the first places we're seeing blockchain technology applied in earnest. So please tune in then. That's going to be Wednesday, August 5th, 2 weeks from now. In the meantime, I highly recommend that you check out the Trust webinar with Drummond Reed. That's going to be a Tech Titans event tomorrow. There's a link, and what I'll do is I'll actually post this slide right now so that anyone can access it. There we go. So I'll be posting this in the chat so you can check out these links. And so check out that Trust webinar with Drummond Reed on July 23rd. If you want to get a meatier explanation of how blockchain works, specifically Bitcoin, I highly recommend checking out that video. That gives you 20 to 30 minutes of very deep detail on how this really works. I base a lot of my talk on it because it was very well done and very accurate. And then last but certainly not least, the Texas Blockchain Council has officially launched their website. And for those of you who don't know, the Texas Blockchain Council is a trade organization in Texas that is trying to promote blockchain and cryptocurrency usage and is working directly with state legislators to get that done and to pass legislation that will encourage innovation here in Texas. With that website launch, we're offering memberships with plenty of perks that come along with it. And so we highly encourage anyone that is looking in the blockchain or works in the space to check out the Blockchain Council and potentially become a member. If anyone has any questions on that, you can contact me at contact@tarski.tech. You can ask about the Texas Blockchain Council. You can ask about the technology. You can ask about what I do at UTD or what I do in my other work. Always happy to talk. So with that, I think we are good. We're at 111. So I guess this is, a question to you, John. Do you think we should do some questions, or do you think we're good to wrap up here?
Yeah, I guess I didn't have to necessarily speed you up. I could have just told people that they can drop, but if you have time, and we can certainly do more Q&A. So ask away, folks, if you have additional questions. And I know there's some out there. It's just a matter of someone typing them in.
All right.
Or even coming off on mute. Well, maybe not. But
Maybe
thanks
not.
for asking the questions during the session too. That was really good. And
Yeah.
Michael gave a lot of good answers, and keep doing that.
Awesome.
Okay.
Thank you. Yeah, thank you for all the
Thanks
kind
again,
words.
Michael. Yep. Good job. Thanks, everyone.
All right. Talk to you later. And
Bye-bye.
I will post a link to the recording on the Meetup page once it's ready.
Thank you.
All right. Talk to everyone later.
Bye,
Till next
everyone.
time.